Okay, now we'll be talking about a more advanced Turing reductions, which involve creating Turing machines inside Turing machines. Okay, so this is not on testable in the midterm, but there are still very useful insight or like intuition you can get from here, especially that to help you with like the basic Turing reductions. Okay, so I think at the beginning I kind of talk about how like the two tips, like the two things that you're allowed to do in creating a Turing machine. One is that you can hard code a constant value, and then the second here is that you can call the deciders that are known to exist, right? So these are the two things that you're allowed to do when you're constructing a Turing machine. Now we're gonna extend this not just to constant values, but also something else, which is like basically the source code of a machine. Okay, so this is what you can do. You can technically, when you're writing a Turing machine, you can create a machine. Very important. Without running it, we just write. Imagine you just write the code, the source code of that machine, and then pass it to the black box decider. Okay, so this is basically a combination of the two things that I said you're allowed to do, right? So how it looked like is that here's an example. I want to use the black box decider, DE, that decides this language, which is a very, very simple language that given a machine, I want to decide if the language of it is an empty set, okay, which means it rejects on all inputs. So and then I want to use that to build a decider for L accept, and you can see why I want to do that, right? Because I want to prove that I want to do this, and therefore prove that LE is undecidable. So this is what I want to do. We want to build a decider for L accept. What we can do here by this is, let's say we have DA for L accept on input. Again, remember the input for L accept is a machine and an input string. Okay, so on input MX, I want to somehow construct another machine M prime. We'll see how to do that, and then we pass that M prime to DE, which is the one deciding this language, and return Sam. Okay, so of course, like I'm sure there are ways that you can do with return opposite, but then for a simple example, I will just return Sam. Okay, so now here's the question for you to think about. Why do I have to create a new machine M prime? Why can't I just use this machine M? Pause the video, think about it, and when you're ready, come back to see the explanation. Okay, so the reason that I have to create M prime is very simple, because the input of DE, which is this decider, must be a machine, right? Look at this. We must pass a machine into DE in order to use it. But that leads us to the second question, which is, why can't we just use this M? The reason is, I don't know like the language of M, right? When I just got a machine, I don't know the language of M. So we can't really prove or like even predict whether DE will accept or reject M. Okay. Again, let's say one more time. This M comes in as an input. Okay. Without running it, right? Because we said we don't want to run. Okay, actually no, sorry, I was talking about the wrong thing. We don't run M. At least for now, we don't run M yet. So actually, like we don't, like even if we run M, it will only tell me. Let's say we run M on X, it will only tell me if it accepts or rejects or loops on X, right? I don't know like what is the language, like what is the set of like all the strings that M accept. I don't know that. And to prove the correctness, to anticipate whether DE will accept or reject, I need to know the language of M. And therefore, I cannot use M as an input to DE. I have to create my own machine. Okay? So now, given that, again, this is how the just a skeleton of our how's that called again? Decider for A will look like, L accept will look like, and we want to somehow construct M prime, right? So again, when you are writing a decider, you want to prove a correctness, right? Which means you kind of want to have this structure. If this input mx is in L accept, by definition, it means M accepts X. Then something happened in this machine by the construction of M prime. I want my decider. I think there is a typo here. This should be DA on M X accept, right? I want because I'm writing a decider DA to accept to decide L accept, right? So I think this should also be DA of M X rejects. Okay, and I think I missed out that because I already assumed that they return SAM. So this here, this means your DE on M prime will accept, and therefore technically the same, basically what I just cancel out, but let me just write it back. Reject, then reject. This is return SAM. Apologize for being very sloppy over here. I will make sure to update my slide. Okay. So yeah, now we want to do this right? So so just pretend that we have it should be DE, and then we have the DA accept, and then we have the DA reject here, just assuming we have that. And now, okay, now we know that DE accepts M prime, which by definition means that the language of M prime is just an empty set. And then here, we want the language of M prime to not be an empty set in order for DE to reject it. Okay? So brainstorm time. So this is our correctness proof draft for M accept X, M does not accept X. Okay, first question. How do we make this happen? How do we make the language of M prime to be an empty set? Okay, yeah, just make it rejects all inputs, right? So this is basically actually what we usually say when how we describe an empty set as a language, right? The machine will reject all inputs, and this is how it looks like on input W. Just reject. I don't even care what W is. Okay? And now, second question: how do we make the language of M prime not empty set? Again, like there are like many answers to this. You can get very creative. That's why I say like Turing reduction is fun because there are like a lot of like creativity that you can do. Of course, like usually we just do the simplest one, the easiest one, right? So one example over here, if we don't want it to be an empty set, then we let it be a set with one element. How about it, right? Just let it have one element. So yeah, just okay, I have duck over here. So let make M accept some input, let's say duck, okay, one input. So the language of M here will be duck, which is not an empty set. And then this is how my machine will look like. On input W, if the input is duck, then accept, else reject. Okay? But there is like a simpler solution. That's why I said there are many solutions. There are like many ways that you can do this, and a simpler one or a more trivial one is to make it accept all inputs, right? So this means that L of M prime will just be sigma star, which is the set of all finite length string. And we have seen this language, we have seen the Turing version of it, which is on input W, I don't care what input W is, I just accept. Okay. So with these two brainstorms, we can fill in the blanks for this, right? We can say, okay, if it is if we want L of M prime to be an empty set, we just let it reject on all inputs. If we want it not to be an empty set, then we just let it accept all inputs. When do you want all these two cases to happen? We want the first case to happen. Wait, sorry. We want to trigger that. Oops. We want to trigger that when M accept X, right? Which is following the one on top here. And then we want to trigger this if M does not accept X. So now we basically have our idea to construct M prime. So this is how it looks like. We just run M on X. If M accepts, then we reject. Okay, so this is basically, you see, it's basically here. On input, then reject, we just reject them immediately. But instead of reject immediately, I now consider if M accept or does not accept X here. Okay, so again, run M on X. If M accepts X, then I reject all inputs. Else, I accept all inputs, which is what we have here. So, correctness proof. Basically, we kind of have everything already, right? Except this two part, which is when M accept X, then this line I like to use. The reason why I like to write pseudocode is because I want to refer to the line number. I can just say we enter line 3 and M prime. I apologize for all the typos. Okay, M prime will reject all inputs, which follows we have L of M prime is an empty set. The E accept and the A accept. M does not accept X means M will accept all inputs, which means, okay, if you want to be more explicit, L of M prime is sigma star, which is not empty set. Therefore, the E will reject M prime because its language is not empty set. And therefore, because we return SAM, we have, return SAM from here, by the way, we have the A rejects. Okay. So yeah, that's all for this one. You have the algorithm, you have the correctness proof, and we're good to go. Okay. So here's an exercise which involves creating two machines, but it is very similar to what we had just now. So I strongly recommend you, maybe after midterm, or because this will not be covered in midterm, right? Maybe after midterm, try this problem, and then I have the solution to it. Okay. And of course, and also the correctness proof. All right, that's all for today. Have a nice spring break and good luck for the midterm.